Right. Namaste, everyone. Welcome to the TAI seminar series, the first one for this year. Today we have Amuchi Ibenegbu, our PhD student, who is in her third year, and it's an interesting topic about mice, not the usual mouse mice, but a form of data imputation called multiple imputation for time series data, and there's a Bayesian approach towards that, and Amochi will be presenting. Thank you, Amochi.
Hi, everyone. Welcome to today's seminar, which is on tBayes-MICE. My name is Amuchi Ibenegbu, like was introduced. And this idea of Bayes-MICE was from our associate professor, Chandra, who talked about mice has been existing, but mice has not been integrated into the Bayesian aspects to capture uncertainty that comes from that. So today we are looking at tBayes-MICE, a Bayesian approach to multiple imputation for time series. So please, these are the content of the research we're going to work on today. First of all, we're going to look at the introduction. Is going to give us the background knowledge of what is missing value techniques, multiple imputation, MICE itself, the Bayesian inference that was integrated into it, the actual tBayes-MICE that we're talking about, some of the theoretical aspects in which we integrated into the Bayesian-MICE, the optimality scaling. We look at the analysis aspect and the concluding aspect of it. So first of all, in the introduction, we're talking about time series. Time series is a longitudinal data set compared to a cross-sectional data set. So the way you handle time series is usually different. You have to consider the time, and in considering times, you have to make sure it's in consequential order. So unlike cross-sectional, you can randomize everything and you still have your result without a problem. Okay, if you randomize or shift things, you miss the actual time sequence of the data. So that's one of the key things where we showed you different cases or patterns that can exist in time series. You can have seasonality, you can have trend, and all these things are what makes it. If you move it, it changes the aspect of the what you're looking at. So what you want your data to be like in imputation, you get to miss that. And that's why we're showing you from the seasonality trend, you can have missing values in these edges. So if you use normal imputation method like mean and everything, you might not be able to capture the trend that comes with that because you're actually just taking average. Are you considering the ups and down movement of the data while trying to do that? And that's why we say time series often is KB towards trend and pattern, but imputation tend to miss this underlying structure. Now, when we talk about missing values, this is another key thing. Most people, when we say missing value, people just assume that missing value is missing values. But there are different mechanisms of missing values. And this mechanism can be classified into three sets, where you have missing completely at random, which we call what? MAC. Or you have MAC, which is missing at random. So when we talk about a missing not at random, which is MNAC. So when we say missing completely at random, which is MCAR, is when missing completely at it just randomly happened, unrelated to the data, unrelated to anything, which can be due to sensor failure, accidental omission, and it has very low bias. Most times the bias is very low. But when we look at MAR, missing at random is always dependent on other variables. So the reason, for instance, today we are missing Ratney. Ratney is a missing values on today's seminar. What could be the case why Ratney is missing? It could be other circumstances. So all those other circumstances are the variable attributed to it. It could be that he traveled for an event. So the event has attributed to that. So it's missing because of observed values or something related to that. So it's just why I said a younger respondent less likely to report income. Because he's a young person, you don't expect him to report income. So it's dependent on the person's age. That's why they didn't that. So you have bias moderate. Now when we talk missing not at random, this is where there is a huge problem most of the times. It's actually missing because missingness depends on the unobserved value itself. So Ratney is missing today because Ratney wants to be missed. That's the case here. So it's missing because it doesn't want to represent itself. I chose not to go today. That's my choice. There is nothing dependent on that. That's someone you're asking to a case where you ask people to declare their income, high income rates. They wouldn't want to declare their high income rates because they don't know if you're going to tax them more. So the decision is on them personally. I don't want to declare that. So you have very high bias because it's dependent on them not trying to do that. So that's why they said Mark is usually less problematic. MNI is most challenging because it's missing, mechanism is linked to missing by itself. But in this case, MICE is missing at random. So the moderate bias. Now, when we talk about handling missing values here, you have two cases. We either ignore the value or you remove it. I have limited number of missing values. I choose to ignore it. Or because I want to actually remove it or ignore. That case, they are just, when I have incomplete case, I discuss them. They're just very small, not much values. I cannot be having a lot of missing values and I discard. So what am I going to work with? I have limited information. And then we impute them, which is filling, when you do averaging and the rest of them that are common. But in this case, when we do averaging, we call it single imputation, just one fixed imputation. That one, it doesn't account for most of the uncertainty that comes with missing values. That's why they said one best guess value is used to impute every other value in that code, which is a little bit of bias. And then you have multiple imputation case, which is where we land here today. So multiple is when you produce different sets of data sets and then use plausible versions of the variables for your, and that's where we are today. So we can say that single gives one estimate, multiple generates plausible data sets to capture uncertainty. Now, multiple imputation process and advantage. These are the three stages of multiple imputation. You have a complete data set, which moves to having multiple imputed data sets. And that leads to analysis and pulling of the results. You pull your result because you want to have a final analysis where you do inferences on the data sets. And that is one of the three stages. And this idea was from Robin's rule, who thought like multiple imputation is actually a very good case. And that's where MICE came from. And one of the key important advantages is that it's going to improve efficiency very well. It accounts for uncertainty in the missing data to an extent or a great extent. And it produces more robust and reliable results compared to single imputation. Now, multiple imputation by chain equation, which is now MICE, where we are. This is the accurate case we're looking at. We impute one variable at a time. That's the condition of man. One variable, it's multiple, so it's a multivariate variable. You can't do one case of that in cross-sectional data. In cross-sectional data, which is the normal data that is not time series, because MICE was made specifically for data that is not time series, that are called cross-sectional data. So you impute one variable considering the other. So if I want to impute that Ratney is missing today, I'm going to consider the fact that other factors are dependent on that and use other variables accumulated to the data to be able to impute that. So it's a dependent prediction. So that is why it said, if I'm imputing X, I have to use X2 and X3 to that, I have to repeat the process until I have convergence. So the first thing I do with mice is that I have initial guess. First step, impute everything with mean or median or interpolation, depending on what you want to do, of the columns. And then I update them using regression, which is what I said. You know the way we do regression, you model y is equals to f of x. So my y is now going to be the current variable I'm trying to predict. And then I use the other variables as my x's for the prediction. That's why he said regress each incomplete variables to predict that. And then you recycle through this process to be able to cover all the variables that are missing. We're going to understand it better. As you go down, you can see the mathematical formulas behind this idea. So, all right. So the mathematical ideas between this is, first of all, we set up, let x run from 1 to up towards xp. So I'm having p variables. I can have income, age, all those stuffs. Those are my variables. And maybe inside age is missing. I want to predict my age. I consider other variables that are in this data set to predict that. So that's why I said we set up this, a set of p random variables with missing values. And then the algorithm runs, which is called a give style update. It's called give sampling. It's literally more like give sampling, but not the actual give sampling, but he took the idea from give sampling. So first of all, I'm trying to update my missing value x1. So whatever I'm updating currently, I'm going to call it x1 t plus 1, right? So I'm missing at x1 at p. So I want to update that. That's why I termed it t plus 1. I'm going to use my x1. I'm conditioning my x1, which is the current variable, with other variables that is existing. I want you to watch something here. That is where it's interesting. I'm using all other variables of that to condition. And then I move for my second variable. Watch what happens. And my initial variable is x2, right? That's the variable x2 that I'm trying to predict the value that is missing. I'm going to still use this variable that I've already imputed in the x1. There is no missing value anymore at that position. That is why it's this, to impute a condition on the rest of them. And then again, I will do that for all the variables. When you reach the rest, you realize that all I'm now doing have all these current variables fully. I don't have any more missing values. I have to cycle through this process. That is why they call it regression switching, variable by variable imputation. That's why I said it is from Robin 1998, Whitley, White, Eppel, and the rest of them. So, now let's go into the actual algorithm. That is the mathematical formula. That's where the algorithm flows. Maybe that will give you more idea what I'm saying. So I have an incomplete data set with p-values. Incomplete means some of them are missing. And then I initialize the missing values in variable x1. I have values missing, x2, I have values missing. I just impute their average mean of each of the columns. All right, I have a complete missing values. None of my data set is missing at this point, right? So now if I want to impute x1, I reset my x1 back to whatever that's missing, right? And I take all observed value within that range and remove the missing one. All observed values within the range of the one that is what present. So I reset back my x1 to missing. I want you to get the point. And then I remove all the missing values within the range of the missing. Remember, the other ones I've repeated them. And not everywhere my x1 is missing that x2 can be missing. So it helps to complete some imputation process stage. So that's why he said for iteration 1 to t, depending on the number of iteration I want to do, for each variable xj, which is missing, I set other predictors, other variables as my what predictors, which we call the features. And then I fit a regression using only the observed values that align with that xj. Only the observed values that align with xj to be able to what? To predict. And then I have a prediction. Some people choose to add noise, but even if you're adding noise at this point, they're all still point estimates. And then I update my xg. I do that for the next variable. I do that for the next variable. It's still one iteration. And then I have, depending on the number of iteration I want to have, if I want to have 5 iterations, first iteration, I'm inputting x1, x2, x3, x4. I go again, second iteration, x1, x2, x3. It's a cycle until 5 iterations, I have one complete data set. That is M1. I go again for another data set. I cycle 5 times. Again for the 5 variable. I have another second data set. That is M3, M2. I do the same thing again. I have another data set, which is M3. So you can have up to 3, 4, 5 separate data sets, which I can choose each and every one of them to do my analysis, because I already have series of cycle iteration that happen in each of the data sets. So I can check each and every one of them. I can check uncertainty from there by checking inferences, checking in between various cases and the rest of them that is there. That's why you say complete data set from the one for pooling or the general analysis. So what are the common challenges that exist in MICE? I've explained to you how MICE work, but there are challenges. First of all, we are using the regression parameters. These parameters are fixed parameters. So regardless of the fact that I run it multiple times, I account a level of uncertainty, but the parameters are fixed, so it is still not set. Uncertainty is still there. And that is why it is not fully Bayesian. And now, temporal limitation, because it was made for cross-sectional data set. It wasn't made for time series data set. And then you have conflicting conditional models. If x1 and x2 are not from the same distribution, there can be conflicting models. So these are what motivated the idea for what? tBayes-MICE. Now, why are we going for Bayesian? First of all, if you remember that when you want to make posterior, you have Bayesian is all about sampling from the posterior. And then for you to sample from the posterior, you need the prior and the likelihood. That was why they said you have the likelihood, which you estimate from your data. You have your prior, which is your initial belief of what you think it should be like. And then these two helps you to have the posterior data. Now, this is going to help us to capture uncertainty with the biases. Uncertainty in the parameters. So in this case, we are looking at uncertainty in our biases. Why I use the word bias or weights and biases, because we are AI models and we do weights and biases. In statistics, they call it parameters, regression parameters. So this has to help us to produce posterior distribution that are not point estimates. So you have varieties of, you sample from posterior distribution, you sample from there. And then this naturally fits the multiple imputation framework. Based on that, this can fit into ideology of what we're looking for. So we are trying to use what we call combined knowledge, observe data to obtain our what? Posterior distribution. And this is Bayesian inference, kind of idea of what I was saying. So if you look at this plot from here, right? This red line or red point is giving us the what we call the likelihood, that is the data behavior, how it is. And then the blue one is prior, what we estimated it to be from the beginning. We believe it should be normal. And then because of the combination of the prior with the likelihood, we're able to get a posterior, which is the black that looks more like the prior, but it's not the prior. That's the idea. So, and this why we say in this case, because Bayesian treats parameters as random variables. So instead of seeing them as a point, 0.5, Bayesian sees them as random. They have to follow distributions. They are seeing them as a random variable. So be able to capture the uncertainty. So Bayesian inference and MCMC sampling, this is where the actual work comes in. So Bayesian, I've explained to you what it's trying to do, but it treats model parameters as random variables to quantify what uncertainty for posterior distribution. And then in most cases, the posterior is hard to what? Generate. It's hard to sample from the posterior itself just like that. It's hard to just do that. So I have to do some technical stuff to be able to sample that. And that is where MCMC comes in. Markov Chain Monte Carlo. It helps us to make proper sampling. It's used to generate samples from our posterior distribution, because I cannot just sample directly from the posterior. I needed that. And in MCMC, we have what we call random walk, which is easy, simple question proposal, and easy to implement, but very slow in mix. And then you have Metropolis-Adjusted Langevin Algorithm. MARA, some people call it Langevin. So they use gradient information, faster convergence sampling. In this case, we tried these two cases to compare their behavior. Now, this is going to help us sample our imputation in Bayesian framework. And now I'm trying to explain the algorithm of MCMC, how it works. This is the idea. I have a training data D that runs X and Y. I have to sample from the posterior, but I need to estimate the number of samples I want to run, iteration samples. So first of all, I have my parameter that is existing, which we call the weights and biases, our theta. I need to initialize that. But this, my weights and biases, it has to follow a certain distribution, right? So we assume them to follow a normal distribution, right? And that's by the way. So I need to propose candidates, theta. Remember that in the new proposal theta I want to propose, I need the initialized one I have plus an error. This particular error that's trying to accommodate also its own case. This error also follows a distribution, normal distribution with 0 and sigma, which is this path, which is this case. So it follows the big sigma. And this sigma, we are assuming that most cases we have, it has to have its own normal distribution. And in this case, we propose them and compute prediction and likelihood. So from this case, I'm going to now use this new generated one to now compute my predicted variable. So once I have my predicted, the likelihood is easy for me to compute. So that is why I said, once I'm able to compute this, I have prediction and likelihood. That's by the way. And then I need to now use this case to compute my acceptance probability, because I have my likelihood, I have my proposal distribution, which is generated from this case, and then I have my likelihood, which I'm going to now use. That is where I generate my acceptance probability with the help of my posterior, which I've already defined from the beginning. I assume it to be normal distribution, and then it follows 0 and chi squared. That's first part of it. And where our chi squared follows an inverse gamma distribution. So we now draw from any uniform distribution. We use uniform because you don't want it to exceed a certain level. It keeps it within a bounded probability, one, which is what you're looking at, because you want to control your error margin as well. So we either accept if your U, which is the one you get from the uniform distribution is less than alpha, otherwise you reject it. This is how MCMC sampling works. So from this process, you sample again, number of iterations you work. But remember, after all this process, the first phase is being removed, which is called the burning. We remove them because the beginning is already biased, it was initialized. So the first stage of your data has not start mixing well. It's still working on the prior knowledges or initialization that you give them. So you remove them so the other part of it can become appropriate results. So this is what I was trying to tell you, right? So that's why I said E from the normal model is the actual model plus E theta, which is an error now follows sigma, 0 and tau square, where this tau square follows an inverse gamma distribution. All right. So this is now our prior sampling. We need this prior posterior sampling, which we got from the likelihood of the theta and the tau square, because once I have my posterior, all right, once I have my predicted value, I can have my likelihood, right? And then this is your prior distribution of the chi and the theta. That's why I said MCMC samples the regression parameter. So in this case, what we're sampling is the weights and biases and the error, which is the tau square. And then each sampled parameter set gives you a plausible regression model, because you're going to sample a wide range of them because it's going through iteration. So you have a lot of them. Accept, reject, accept, reject, accept, reject. So all the ones is accepting is keeping them. At the end of the day, you have values up to the number of samples you want it to. Then MCMC can be used to train the models as well in linear regression, neural network, and that is what motivated this idea to use mice. Since it can be used to train regression, and now mice is doing regression, then you can equally use it to integrate that. So missing values are going to be imputed from the posterior predictive distribution. Now, this is our likelihood model. That's why I said once we get this is the predicted value. So once you have your predicted value, it's easy to get your likelihood straight up. And then you know you have your tau already. And tau from the beginning be initialized as the same way as you initialize your theta before the whole process proposal starts to run. And then in this case, we're assuming that our prior is on a Gaussian model, right? The weights are coming from a normal distribution and the prior which are coming from the inverse normal. That's why you said these priors allow flexible modeling of certainty in both parameters. Time series mice. Before we go into tBayes-MICE, we thought of the idea, since mice was made for cross-sectional cases, right? And it was the multivariate case. If it's time series, can we also do it for one variable case? So this is a case of time series mice one variable case. We thought of it, if we integrate it, how do we do it for when it is just one variable, right? So if you have multivariate time series data set that is a system, right? And then for xj, I have just one variable, xj, that has its own missing value. How do I get the response variables? How do I get predictor variables? And then the key idea is to use temporal information as predictors in this case. So we are trying to include past and future lag. So we are using the idea from Brits, bidirectional. So we're doing bidirectional lag. Use both front and back. Because this is not prediction, this is imputation. It is allowed to do back and forward. If it's prediction, it has to be strictly forward and not back and forward. So, and now what are we going to use our temporal predictors in this case? We said we call the whole predictor variable as our tx z t minus j, whereby we have xt minus j, which is the actual order variables. In this case, is the one variable. And then we take the lag of the past and the features to make it a complete variables. So makes it a multivariate variables. Once you take the lag, past and feature of the words one single variables, you have a multivariate variable, but it's generated from one variable. And that is why we have a condition of these for the time series and single case. Now, the actual tBayes-MICE, this is where we are. For each variable xj, model observed values given that orders t underscore j, right? Minus j. We are going to condition them. If you remember what I told you from the Bayesian aspect, we are going to condition them. This zt minus j is going to generate from our other variables that I showed you from the beginning. This one, this temporal factor, right? That is where we generate it, regardless of the xj we're doing. So once I consider my current xj minus 1, my current xj minus xj, this one, is going to be all the variables that are not my xj. This is in the case we are doing with multivariate, because what we are doing is actually multivariate. That is our z. This is how you construct your ztj aspect. So I'm going to now get whatever I got from my proposal of the Bayesian aspect I told you about, whatever I sampled from MCMC, which is our theta, j, and tau aspect. If you remember, I told you those are the key parameters you're trying to make Bayesian. So once I sampled them, in that case, my current model is going to be conditioned on this, and that follows in normal distribution with those parameters. And that's why tj is regression coefficient, that is going to be what? Gotten from the Bayesian sum, as well as the tau, which is the reciprocal variance. Now, our prior is still going to follow the same prior knowledge of tj following the normal, dash we are still following an inverse gamma p1. So we are going to assume a weakly informative prior, right? Because we want our data to dominate the information. That helps what you're trying to predict. So that at iteration s, I'm going to obtain a possible theta of number of x's, right? I'm going to have theta j of up to the number of samples and tau square of up to number of samples, which I'm going to sample via random walk and via Mala, and then impute our missing values. So our missing values is now going to follow a normal distribution. Since our observe is following the normal distribution, the missing will equally follow a normal distribution condition on this. But in this case now, based on this, obtain theta jx and tau square x. Because we are using from this initially, and then now after sampling, we're going to impute it this. With this, is able to capture both parameter and predictive uncertainty. I'm not just capturing parameter uncertainty, I also capture imputation uncertainty. So another interesting aspect of it is that, do you remember when I said that I'm going to go back, that will give us a better idea of what I'm looking at. Do you remember when I said that this tilde, this stuff, follows theta and sigma, big sigma? Now, this is an interesting aspect of it. It was because one of the key problems of MCMC is convergence, right? So if it doesn't converge well, it means it didn't get to a stable place. There was no proper mixing, or you need it to actually converge. So there is a study, key important stuff that helps your convergence. That's one of the key things I also learned from this. So to estimate this proposal distribution, which is the error that we're adding to this, there is a research about optimality scaling principle. This optimality scaling was from Robert et al., which suggested that if you have a sigma proposal that is up to 2.38 square divided by theta number, the column number or the total number of that, plus the targeted one you have, that you are aiming acceptance criteria of 0.234. That's 23.4%. That if you get this optimality acceptance, you are probably going to have convergence. I was surprised to see that, try to implement the theory, and I was surprised to see the convergence was talking. So, also, this adaptive strategy, optimality scaling, and then they extended the optimality scaling to what they call adaptive strategy. Considering the data case, when you have sufficient data, you use when your N is greater than D plus 5. So maybe my column or data is more than plus 5 is up to this. So I estimate it, putting a little bit of Excel. This is my minor increment. You don't want it to be 0 or something, so this helps it not to go towards the 0. That's when you have limited data, you continue with the initial idea. Now, for Mala, Halio et al. Also estimated. So for random walk, you are estimating your acceptance in terms of the acceptance you're looking at. I like to go back. That gives you a better idea. The acceptance you're looking at is this acceptance of theta and the rest of them you're looking at. How are you accepting them and rejecting them? So this optimality scaling is telling you that if you have aim optimality scaling, aim your sigma to be following this format. If you aim towards 23.4%, that you can have a proper convergence. And then the Mala, if you look at and aim at 57.4 following this condition given there, that you also have convergence. So Mala uses gradient information. The MCMC I showed you was for random. Mala uses convergence. And then higher acceptance due to informed proposal. So it's now informing from your data. It tells what. So this is very efficient in exploration of the posterior. So this is our framework for the data. So we are going to have incomplete data sets. This is us. We are trying to dictate the time series pattern that is existing. So what we did is we have two cases. We want a case. If we dictate it and there is linearity or time series, impute it instead of using simple mean, because it's a time series data, impute the initial guess of mice with a simple time series like interpolation or other stuffs. Just do the first initial interpolation. And that's what we call initialization. And then you follow mice iteration using the condition. You have the design matrix construction. We already explained this, where you consider other variables other time constraints like hour, daily, depending on the condition, and the lag variables of your current variable you're trying to predict. And then from there, you now define a Bayesian model. This Bayesian model is now going to integrate all our experience, explain the theory, which will now lead you, that's the proposal of X random walk or Mala, depending on the one you're doing. And then you adapt proposal scaling, reject or accept each one. And that will give you your sample and input posterior of your missing value. You have a complete imputation. That's the framework. So this is the algorithm in interpretation. So we're going to create a copy of X from X and fill missing entries using estimate. If you understood MICE, then it's easy, because the only place you're integrating things is Bayesian aspects. Instead of putting a point estimate, we just replace it with what? Bayesian. So we have, and then you have a temporal predictor. So you have temporal predictors being constructed. I'm sorry there are so many mathematics happening, sorry about that, or so many theory parts. So you have this integration, we are conditioning them on leads of what? Other variables, on leads of our current variables. So this is coming from what? The other variables, this can be hourly, coming from hourly, daily, dependent. Then the lags, and then you have exchange. So you update, fit your regression model using observed entries and samples, which you get this, whereby your error is going to follow what? Theta tau square. And then you sample parameters via MCMC that I've explained to you to get this theta. And then it imputes your missing values. You can repeat this for a number of k iterations to generate imputed datasets. So first of all, before we went ahead, we tried to show a case of what? Univariate time lag. If you remember, I explained when we have just one variable in time series. So we tried the case, compared it just when we just have one variable and use the lag to do that, without even considering Bayesian. This is not Bayesian, just MICE, time series MICE, just that. Just one case, variables, use the lag to predict. Just that alone, you could see that MICE is actually a powerful imputation model. It beats linear interpolation, K nearest neighbor, mean imputation, media seasonal decomposition, LOCF. It beats all of them by root mean square error, mean, and the rest of them. From here, you can see that time lag must achieve the lowest error across all metrics. And that means that incorporating temporal lags improved imputation. So that was like the first stage. If we incorporate this, will it actually help imputation? You could see that it actually helped over standard. So the traditional model didn't actually do so well. So now, from that, we wanted to look into our convergency model. So we looked at convergency model of random walk and Mala over two cases, right? And we tried that over two chains. So the first one is the first and second chain of random walk. Now, you want the first and the second chain to almost come from the same range. If you look at this, these are first and second chain. You could tell that it started from 0.6, first chain, and ended at 0.9. This is for the most key parameter, which is the error parameter, which is tau square. It started from here, and the second chain, the same thing, from 0.6 to 0.9. And you could see that is actually the tracy plot is moving in the accordance. There are no spike over spike or something. And then you could look at the density plot is normal. And it runs from 0.6 to 0.9, interestingly. And then, interesting thing with random walk, for the two chain, you can see that both of them mixed well. So they're almost within the same range. But the interesting thing is that in the beginning of the autocorrelation, there were very high correlation factor in random walk. But as it gets to lag value, it's converged. That's the convergence you're looking at, which means the optimality scaling we implemented was perfect. But the only interesting thing now, when you look into Mala had more hairy tracy plots compared to random walk, which means Mala explored the space more. than Random Walk did. And you could see they are still running within the same range, even after all the exploration. Still got to the same range as Random Walk. It went from 0.272 to still 0.92. But this is from 0.6 to 0. And then when you look at the density plot, it runs from still 0.6 as of Random Walk and still ended at 0.9. But autocoloration converged from the beginning of the lab. It had a quick convergence because Mala always converged faster than Random because he uses gradients information. And that's why Mala achieved faster convergence, low autocoloration compared to Random Walk, which means it led to more posterior exploration, efficiency of that. So you explored everything. Now, to confirm this, we have what we called MCMC summary statistics. You wanted to compare, did my model do well? Did this MCMC actually compare? There are so many statistical models aside visualization. So you needed to use your RCAP, which you are going to use. You want it to be less than 1.05. In our case, we had all one. This is for one variable, because I can't show you for all the variables. It's so much variables that we tried, but they were all having good convergence. But the key parameters you need to look at is tau. If you look at our tau, he had 46,000 number of what bulky sample used. And if you look at Random Walk, you had 2,535, which confirm our plot that this had more exploration. Mala had more exploration because it's having 46,000. Meanwhile, the Random Walk is having 2,500 something. Now, the mean runs within this range, and you could see they are within a particular range. At the end of the day, both of them, interesting thing, are converging in the same way. Look at chi-square mean, 0.563. Look at Random Walk, 0.564. Regardless of how long or how slow Random Walk was, it still converged to almost the same point as Mala. So the convergence was working for both cases. And that means our optimality scaling of telling you to estimate this part. Because even I could have showed the optimality, the acceptance optimality. You will see them having 21.5 accepted, 22 point something accepted, rejected. You will be seeing that optimality was actually aiming towards that. And now this is the metrics. This is the metrics of the data we compared for the Bayesian-MICE. So we compared this with MICE itself. We compared it with BRITS, which is a time series data bidirectional model. Like, it's very popular in its own way in terms of I think it's a deep learning model itself. So we compared them to see how it behaves as well. And then from the look of things, we had 6 variables. That's why I said it had a lot of results from this model, but you can only pick 1 or 2 variables and present them. You can't present everything. So you can always check them out on the GitHub because I put all the plot results there. So you can check this variable. That's why we use this line to outline. The red is going to show you the performance. And you can see the gap between the BRITS in terms of mean absolute deviation or mean absolute error. You can see the gap between MICE, BRITS, and what? tBayes-MICE. For all cases, there was it was high, it was very low, error rate was very low, which is what you're looking at. It was lower than the rest of them. It had a very good case. Both on all the variables, it was actually beating each and every one of them, including in the case of Mala. So if you look at the result of Mala, that is where I also wanted us to look at. You can see that Mala was giving us 0.266, this was giving us 0.266. They were having almost the same result. Almost same result. Except you have, like this case, we have 0.1. Okay, these ones are going to be deterministic because they are the same. But in our own case, we have 0.1349. And then Mala is giving us 0.1346. Are you seeing the case? They are still within the same region of error rates. And then this one, the root mean square error is the same thing as on both cases. So regardless of the MCMC used, they converge to particular states because they were having almost likely similar results. But we wanted to compare how their convergence works. And you can see from here, it doesn't matter sampler you use, what matters in the convergence. But what you are aiming is, since smaller is faster in convergence and explores better, why don't I use what explores better and the rest? But that's the case, we have to explore the two cases for this variable. This is for air quality data set because we tried to data set. Another case was physio data set. It's a clinical data set. And then you look at the same case again. In this case, Brits was very improving. It was very competitive. That's the word. Brits was competitive to the model. But in cases of what these two variables, WBC and what, you had the cases and you can see that Brits had beaten tBayes-MICE in this particular variable, but in terms of mean absolute error. But in root mean square error, the tBayes-MICE was still beating it. So it was like these two variables where it had a more temporal variability. The air quality data had temporal cases, but there are more temporal variability in physio data sets. And that is why you could see the capturing differences. And then, but in other cases, Brits was very competitive, but our model was leading it. Now, summary of the results. The air quality data, you can see actually our Bayesian model in the air quality data achieved the lowest mean absolute error and root mean square error. We are taking the normalized cases across all variables. And then both random walk and Mala produce very similar results. We have lower standard deviation, indicating stable performance across runs because we have 30 experimental runs. That's a lot of experiment because MCMC takes a lot of work. Then we have PhysioNet. The physio data set, the same thing. It's improved over mice or variables. Strong gains observed from these variables. But Brits is very competitive for some of the variables, just like I was equally explained. So therefore, temporal Bayesian model is improving our accuracy and robustness. Now, this is the table aspect of it. Let's go into the visualization aspect of the model. Now, we look into the prediction accuracy of the variables, right? For each of them, this HCO3. When we look at these variables, I want us to look, because that's where you will now see the actual performance from the visualization. If you look at the predictive aspect, you could see that our model was way more within when you look at the true values against the predicted. When you look at the residual, you will see that there are so many stack of mice as well, right? And breeds as well, spark. But the green one, which is our model, is actually compassed within the same place. But one interesting aspect is that when you look into this particular model, you could see a pulling of the breeds down. It pulled up. There's a lot of quick, sharp drops. So it had very cases of quick, sharp drops. That is where the error margin was very high. But our particular model was almost consistent within the same error. We'll confirm this when we look at error. And this is for the case of the air quality data. This is the physio data. In this one, you could equally see in our predicted model, all was almost within the fitted down. And then for here, look at the residual error. You could see this is pulling down more. That's breeds. We can't talk about mine, so this is fine. But when you look at this box plot, that tells you more where our tBayes is very low and it's way better consistency. That's why you said it's achieved tighter residuals, lower error variability, and more reliable prediction across most of the variables. Now, compare based on what we're talking about the error. This helped us to do more of error imputation. We want to check the error comparison, imputation error comparison, and that's where you could see the proper spike. So we have the yellow, which is a mice. You can see how spiked it is. So we want the error to go to 0 as much as possible. That means the error prediction reduces. But you could see mice spiking down more, both negative and up. But our breeds as well has its own spike for this variable, but ours was within a very limited error rate. Similar here, you could see breeds have very spike for air quality data. It had a lot of spikes out. And you could tell from the imputation error, that gives you the error margin, how it is. What's the error margin? How close is it to 0? But you could tell. And that's also for us to be assured that what we are getting is actually giving us a good result from the posterior. So we look at the posterior performance, posterior predictive performance. We know we're going to generate series of what? Variables. Let's check the posterior behavior of the performance. Because the one we just, based on the imputation, you can only sample one or take the averaging of all the posteriors you have. Maybe you can sample a range of 5 and then impute them, right? That's one of the cases you could do, or you could take averaging of them. But now we want to look at the modeling behavior of all what was sampled. The confidence interval. Was it within the range between the train and the test model? And then we looked at it. You could see our train was, the blue line is the observed value. It was following the observed value almost perfectly, right? According to the model. And it was still within the confidence interval line, which are this margin gap that are very small, because the confidence is giving you a very small margin. But you could check it to confirm. That's why it's a good fit with uncertainty captured around the observation for the train. The test is where you actually do the proper what? Strong generalization of calibrated what? Uncertainty. And then you can see ourselves the same thing on our test, following the blue line traceably what? Well, which means the posterior was actually from a proper range of the words, the actual value and the missing one. And that's why we say captures both the data trends, uncertainty, achieving fit on the train, and reliable generalization. And that gives us the experimental summary of the model. But this is one of the experimental summary of physio data. You can check that of the air quality data on the top as well. So we can tell from we just give the proper general summary of how we predicted. And you can tell from the back, mine was quite very high error. You could tell from there. See how far it is right away. Breathe was competitive, like suggested, in these two variables, but in the other variables was low. Just like the other one where you see the air quality data, you can see how gap of it is. And then for this case, from the box plot here against the root mean square error generated, because this is after 30 experimental error, the summary of what we have. And then you could see where our box plot is down without any out of the outliers of the rest of them. And in that case, we can see that tBayes-MICE achieved the lowest root mean square error across all variables, consistent accuracy gain over mice and breeds, more stable performance. And that brings us to our conclusion. We can say that in this model, we are introducing a full Bayesian formula of mice for time series data, allowing inference of the model, parameters, and missing values. So we are doing both inference, that is capturing uncertainty, both what of the parameters and missing values through MCMC sampling. The proposed method not only incorporated temporal dependency via bidirectional structure, but also ensure that the framework initialized stage is time aware, because we are doing the first stage to what time aware. Through the generalization of the posterior predictive distribution, our model captured imputation uncertainty that is often ignored in most existing methods. Empirically, we can validate the evidence. You can see we validated it, and it should improve performance accuracy compared to other conventional. This can also be applied. We apply in environmental and clinical data sets, because we don't just do one data set, we try it in two different aspects of that. And future work, we are looking at, if you remember at the beginning, I explained about missing node at random. That's interesting. And we're looking at extending this particular mice to spatiotemporal mice first. That's the first case. And that is going to be missing at random still. And then we extend this Bayesian mice that we had to spatiotemporal case. So we want to do just simple mice to spatiotemporal case. But there's a lot that will happen there, because currently we don't have anybody that is spatiotemporal mice. So we're looking at extending this to spatiotemporal mice, take this Bayesian mice to spatiotemporal mice, and then take this same Bayesian spatiotemporal mice to missing not at random if we have the energy. Because that's a lot of theoretical work and background, but it's still achievable. We can try that. So I'm going to thank Associate Professor. This is like so my supervisor, that Associate Professor. Wow, that's so good. Associate Professor Roni Chandra for this wonderful work. We had together back our thoughts, but we're able to do that. And thanks to my second supervisor who is not here, but also have very great impact on the work. So thank you so much. But before you clap, I'm going to take you to the GitHub. Yeah, so we can look at the GitHub. Yeah, so I'm going to share my screen again. All right, so this is our GitHub, right? Which is organized in datasets. When you go in here, you're going to see the dataset we used. The actual AirQuality data from UCI repository, which is also popularly used in missing values. You are going to see the physio data sets. This requires a lot of work because the way the data is not in Excel format. You have to convert it into MA, because you have to use logistic modeling to convert it into MA, missing at random, compared to this that I just did missing completely not at random. But this case was missing at random, right? So because mice can run cases of missing completely at random and missing at random. That's one thing with mice. So these are the data sets we use, and then from this data set, we created a subset of data set that is not missing. And then we have masked our own missing values into this case, similar to the other case. So how the maxing of the physio data was done is also here. You can check it out in the code aspect. Yeah. If you go to the physio data reader, you will see how it was maxed. You can see where it did mark, did missing at random. You see the way we use logistic regression to be able to mark that and then extract the data. Because the way it was, you need to extract it and form it into Excel sheets so that it can form an Excel sheet that helps us to do that. So we have our Breeze model, which we use to compare. This is our Breeze model run through GPU, Katana. Thanks to Katana, yeah, UNSW Katana. Because otherwise, this model would run in my computer for more than 1 week for one of the data sets. But Katana can reduce the work for you. Pay for this and it's done. And because it is not a CPU, right? I'm looking at extending this to be a GPU model in our next work. I wouldn't want it to take longer procedure as it did with this one. So these are the cases where our MCMC chain, this is the MCMC. And this MCMC you can read MCMC paper by Roni Chandra. Yeah, you will see the code acceptance. So we use the MCMC code from there and then augment and integrate the optimality, scaling, and the rest of the stuff we did. So that I had already a basic ground of the MCMC. You should read that if you want to have knowledge about MCMC. It's a good one. At least guide you on the tutorial on how to do that. So this is our simple MCMC where we'll now create the lag. And then from this process, you created the lag. You have to start sampling, time initialization. All these are some of the functions of what happened. And then for the univariate mice lag, this is where you have that. This is the easy one. Interesting aspect is when you run a single MCMC mice under this. So that is where you call some of the functions, because all these are Python functions and I call them out. Once I call them, it runs on itself. So, and then for the visualization case, yeah, we have a lot of visualization that came out from this. So this is like one of the most big aspect of it. The visualization was a lot. So if you go into this plots, like I said, you will see, like we already saw this one, you can check convergence summary of the other one. You can see the summary as well. Yeah, you can see summary of one of the variables. You can see that it is less than 1.0 and 1.05. You can look at the, you can get the which means square error. You can check a lot of them. This is one of the variables. So a lot of stuff, you can get all of them. So you have different cases or different imputation comparison or stuff put in there, which you can take your time to check out most of the stuff now. Thank you.
Okay. Thank you, Amuchi. We can take some questions, comments about Amuchi's work. Anybody here?
All right.
How hard would it be to GPU accelerate this whole process?
Is it?
How hard is it to GPU accelerate this whole process?
How hard it's going to be?
Yeah, for GPU.
Because this is currently we're using Pandas NumPy.
Yeah.
So you need to change it to be a TensorFlow or PyTorch.
Yeah,
So
okay, but would it be
PyTorch,
difficult? Is it difficult to do that? Refactoring the whole thing?
I think it might be, but I have to. It's better you take the pressure than having to take longer time.
Yeah, okay.
But it's still going to be okay.
I think there are some libraries that transform NumPy operations to GPU.
Oh, they automatically do that?
Yeah.
Oh, really? Oh.
Yeah.
It shouldn't be too hard.
And then you can use tBayes-MICE as well. I think they have the MC adaptive.
I have a question for you. How much of work will be needed to be done to transform this into an actual package, Python package that can be used by people?
I haven't thought about that, but it seems like something we have to look into. Yeah, I might have to look into that because MICE already has a package itself. You can use MICE as a package. So if it has package, yeah, we can.
Yeah, something similar to MICE.
Yes.
So can be used by the Python packaging platform. Yeah.
Oh yeah, maybe I have to look at how MICE was packaged.
It could be a small software pipeline in the future for this packaging.
Yeah, we can look at how that was done, then we can have that.
Other questions? Yeah.
Sorry, I just have one more. Maybe you touched on this a little bit earlier as well, but you were drawing up confidence intervals for the under the test thing. If you one slide.
Yeah.
I mean, I'm not entirely from a time series background, but I just had a question. Typically, whenever I've seen forecasting from the time series model, I've always seen the confidence intervals to constantly keep on deviating further and further away. So why is the confidence interval so narrow as you keep on iterating forward in time?
It's a bit narrow because you are doing posterior, right? You're sampling from the posterior and you actually did optimality scaling to make sure that you are trying to have a proper convergence and is within a proper range of sampling. So the narrow range, and remember, this is actually more expanded here, expanded in the test compared to the train, because the train has been an unseen data, has been a seen data. But in this particular case, it's unseen. So therefore, that's why you see a little bit of larger. But it depends on, because it's sampling from the posterior. This is posterior prediction, not the actual time series model.
Oh, right, okay.
Does that make sense?
Yeah.
It's from a posterior of the parameters of your estimated parameter model, what you looked at, not from the entire of the data set. That's why it looks like that. That's
okay. Okay, cool. Yeah, the time step bit confused me, so I wasn't sure.
Yeah, it's okay.
Yeah, okay.
Because they are looking at the time step at each of them of the posterior sample.
Okay.
Yeah, according to the tree, that's why it's called predictive performance, using the predictive performance. Thank you for that.
Right. Anybody else has a question? All right. Any comments? Okay. Okay, then thank you, Amuchi, for a wonderful presentation, and we can end the session then. Sorry, any questions from online? Anybody has any questions online? Anybody? You can also post in the chat. All right, so don't seem to have a question online.
Okay.
So next week we'll just have a internal presentation by Ren. It will be on Teams. And then after next week, I will give a seminar presentation after next week, hopefully. Thank you, everybody.
Thank you. Thanks for coming.